methods. As you remember, last week I told you that it's the starting of this course starting this week from the roots of the equation. And this topic of roots of the equation will continue with us about 3 weeks. It's very important because question number 1 at the midterm and also final exam, it's coming from this part. So at the end of this lesson, you will be able to identify and apply the practicing methods to solve and find the roots of the equation. So the first thing before we start is what's the definition, or actually what's the roots of the equations, what we need to do here. So the roots of the equation is obtained at the value of x when the function is equal to 0. So in general meaning here, what we need to do here, we need to try to find the value of x that is going to make my function here is going to be equal to 0. So I need to find this value. Okay, this is what we are looking for. Try to find the value of x that when I put it or substitute inside the function will retain the value for me here. It's equal to 0. Okay, so before the digital computer, roots of algebraic transcendence equations could be found by direct methods that can be solved analytically but not easy for complex function. Or by the easy way, it's by plotting the function and determine where the function is crossing the x-axis, but this one is lack of precision. So these 2 points, we are going to talk about it later. But now it's what we need to focus on here. It's we need to focus on the first point, which is root of the equations. It's we need to obtain the value of x that make the function equal to 0. So roots of the equation is going to be have 2 types of methods. Today, we're just only going to cover the bracketing methods only. Next class, which is going to be on Friday, I'm going to talk about the open methods since we are not going to have a lab this week and we cannot use the MATLAB online. So I'm going to cover the open method. I'm going to cover the open methods on coming class on Friday. To replace a class, we can. If not, I'm going to give you some videos how to make the open methods on your future. So now let's back to the class in here. Today we are going to cover the bracketing method. So we are talking about the bracketing methods. Okay, so what's the difference between bracketing methods and open methods? Bracketing methods, it's the method that start with 2 initial guesses or 2 initial values. Normally we call these values is like x lower bound, x lower, and the value of x upper, x upper. Okay, so you are going to start with 2 initial values. So this means when the question is coming from this part using a bracketing methods, you will notice that the question is providing you 2 values. One of them is a lower bound and one is the upper bound. And in between them is the value of x that we are looking for. So in between this x lower and x upper, there will be the value that we are looking for. So we are going to find the values in between x lower and x upper. That's why we are saying that this method is called as a bracketing methods, because the value that we are looking for, it's bounded by x lower and x upper. So as a definition for the bracketing methods, it's a method start with 2 initial guesses that bracket or contain the roots. So this value here is the root. Then systematically, we are going to reduce the width of the bracket till we are going to find this point. Open method, this is what we are going to cover it on next class. It's a method that involves systematic try and error iterations. So here, no need, nor necessary, because you are going to have 1 initial value, so that means it's not considered as a bracketing methods. Okay, so graphical method, it's one of the bracketing method. It's a very simple methods to get an estimate of the root of the function when it's going to be equal to 0. So what actually is the graphical methods, what we are going to do with it? By the way, you are not going to have any question coming from the graphical method because it's very easy, but it's what's the use of the graphical methods? It will help you to get some side of where is actually the root it fall off. So the function, we are going to be plotted against the x-axis, and where the location is the function is crossing the x-axis, this is will give us the root. So for example, if I'm going to have this y-axis and this is x-axis, so this is x-axis here, this is y-axis, which is actually is the function. So let's say that you are having a function. That function is, when you are going to plot it, your function is giving you this curve. So when the function is cross the x-axis at this point, so this point here is considered it's the root. This is the root of the function. Why? Because the function is crossing the x-axis at this point. So this value here is equal to 0. Okay. So the graphical techniques, it's limited practical value. It's not precise, because if I just make it right now here, if this value here is 0 and this value here is 5, this value here is 5. Okay, so can I ask you a question here? What's actually is the root of this function? Is it 1? Is it 2? Is it 2.5? Or is it 3? Nobody can tell. But roughly here, we can say that it's the root. The root is between the value of 0 and 5. So this is the function of the graphical methods. It can give me a roughly estimate where actually is the root. So if someone is asking you why you are not going to try to find the root of this function at the value of x is equal to 6 or 7 or 8, actually the answer is going to be wrong, because actually it's the root is between x lower 0 and x upper is 5. Cannot be at 6 or 7 or 8, or cannot be in negative value. So graphical techniques, it's limited because it's not precise. But we can use it to obtain a rough estimates of where is the root. Okay, so for example, and by the way, we are going to follow this example for the whole class today. We are going to use the graphical approach to determine the drag coefficient C needed for the parachute of the mass is 68.1 kg to have a velocity of 40 meters per second after free fall with the time it's 10 seconds. And you are having the value of the gravity is given, it's 9.8. So we are going to use this function here, and we need to try to find the root of this function when the value is going to be equal to 0. So this means we need to find the value of C that make this function will be equal to 0. So of course, we don't know at the beginning what's the value that can make our function is equal to 0. So let's say we are going to start from 0, 2, 4, 6, 8, 12, 16, 14 till 20. Okay, then we are going to plot the values. So when the C is equal to 4, you are getting to put the value of C here. So you put the value of 4 and you make the calculation. So you are going to get the answer that it's the function of the drag coefficient will give you the value of 34. So this is the value here. This is when C is equal to 4. Try when the value is equal to 8. So you will back to the function here. So instead of the 4, you are going to substitute the value of 8 here. So you are going to get the answer, it's 17.65. So when 8, the answer will be equal to 17.65 here. And again, you are going to go for the value of 12. So you get the answer is 6.06. And when it's 16, the answer is going to be get negative 2.2. And when it's 20, the answer is negative 8. Okay, remember when we are saying that it's for the graphical methods, when you are plotting the function, when it's crossed the x-axis, so So that's mean this value here is considered is the root of the function. So this value here is considered it's the root. Okay, but remember that we are saying that it's difficult, it's not precise. So I'm not sure if that value is 12.5, is it 13, is it 14? I cannot be sure. But the good things in here about the graphical methods, now I can tell that it's my value of x lower, the value of x lower, here it's equal to 12. And the value of x upper or the upper bound is equal to 16. Here, 16. This is the one here, 16, 1, 6. Okay, so if someone now is asking you why you are not trying to find the value or the root between 4 and 8, cannot be. You have to start from the value of 12 and 16. So it's going to give you the lower bound and the upper bound. Okay, there is something here also, even if you are not going to make the figure or you're not going to make the graphical method itself, you can look at the table here. The table here, when C is equal to 12 and C is equal to 16, you're going to see that the function is changing sign. So this is from positive, it goes to a negative value. So when the function is changing the sign, so this means it's the graphical methods, it's have been happen and it's crossing the x-axis because it's changing the sign from positive to negative. So this means it's your curve, it's already crossed the x sign at 1 point. So in my case in here, I can know that this is my x lower. And this is the value of x upper. So this means even though that I'm going to make the curve, when I see this, the function is changing the sign from positive to negative or negative to positive, this means it's crossing the x-axis. So I will get the rough estimate of x lower and x upper. Okay, so that's all for the graphical methods. Do you have any question about it? Is it clear?
Clear, Doctor.
Okay, so here's some cases, but it's out of our range. We are only going to focus on them. Like the first case in here, that the function actually is not even crossing the x-axis, so this means this function has no roots. This case in here, when the function is crossing the x-axis at many points, so point number 1 and point number 2, this is we are going to cover it at week 4. So we are not touching this today or this one today. Today we are just only going to cover a function that has different signs. So let's say from positive to negative, which is having a single root. So we are going to use the methods to solve this case on today. The other cases in here, we are going to have it in different chapter. Okay, our first methods or our first question is coming from midterm exam or final exam. It could be happen coming from bisection method or false position methods. Okay, so now from the graphical methods, we have found that it's the function when it's continuous and it's changing the sign. It has an opposite sign. So that means the function is crossing the x-axis at 1 point, which is this one is the real root. We know that it's the function has one root, so we are going to find it using the bisection methods. So how is this method it works? Since you are going to know here, it's the value of x lower, it's the value of x lower, and here is the value of x upper. The bisection methods is going to be creating an intermediate value, we call it xr, x root. So the methods of bisection methods is going to be creating a value, we call it xr. This value xr, it's in between x lower and x upper. It's exactly in the middle between x lower and x upper. So we give it the blue dot here. But actually, it's this value of XR here. It's supposed to be closer to the red dots in here. So it's supposed to be, we move it to match the red dot here. So by systematic procedure in the bisection methods, we are going to iterate till we are going to match this value of XR or these blue dots to be matching the real, the red dots. How actually we are going to do this procedure of the bisection methods? This is the steps how we are going to move that blue dot to match the real root or the red dot. So what's the procedure of the bisection methods? First one, you are going to choose the value of X lower and the value of X upper. But actually, in your case in here for our course, you are not going to choose the values because the question when it's going to be happen is coming out from bisection methods or force position methods, the value of X lower and X upper, it's going to be given in the questions. So you're not going to choose the values by yourself. So X lower and X upper, it's going to be given in the question. So X lower and X upper is going to be given. Here, the first step, you are going to calculate a new value of XR. How to get the value of XR? Remember that XR, it's a value that it's between X lower and X upper. It's exactly in the middle. So it's equal to the initial value of X lower plus the initial value of X upper over 2. So that's why you're going to get these blue dots here, which is we call it XR. So now you want to check if the value of XR is matching the real root. So you want to check if this blue dots it's on top of the red dots. How you are going to check that? By having these conditions. If the function of X lower times the function of XR is less than 0, so you're going to narrow the search. So for the next iteration, XR is going to be having the value of X upper. Then you are going to repeat the same steps back again by having a new value of XR and in the middle. Then you're going to check again. If the function of X lower times the function of XR greater than 0, so for the next iteration, X lower is going to be taking the value of XR and you are going to repeat. For how long you are going to repeat these steps? You are going to repeat these steps till the approximate percentage relative error it's less than the tolerance value is going to be given in the question. Let's say they are asking you to repeat till the error it's less than 5% or less than 1% or less than 0.5%. So each time you're going to iterate, you have to calculate the approximate relative error. How to calculate the error? XR new or the new result minus the old result over the new result of XR, as I taught you last week. How to calculate the approximate error? The new result minus the old result over the new results. Okay, when you are going to do the example, you are going to understand that, and by yourself, you are going to do the exercise. So remember, we are going to use the same example. So we are going to use the bisection method now to determine the drag coefficient C needed for the parachute mass is 68.1 kg to have the velocity of 40 meters per second. And here you can see that it's the value of the error, it's or the tolerance value acceptable. It's given here. You need to get the error less than 0.5%. And there's one extra information here. It's given to us, which is the true value. Since the true value here it's given, so that means I can calculate the true relative error. In this procedure in here, you are calculating the approximate error. So you have the XR new minus XR old. But since the question here is giving you the true value, so that means you can calculate the relative error. The relative error, that's mean true value minus the result over the true value. So you can calculate. So you can calculate here actually two types of error. You can calculate the relative error and the approximate error. Okay, so this means the answer that we want to achieve, or the real answer, or in our case here, it's the red dot here, that it's the real root. It's supposed to be the answer of 14.7802. This is the value that if you substitute here, you are going to find that this function is equal to a 0. So now let's try how we are going to get that answer. So first, you are going to guess two initial values, which is the value of x lower and x upper. For us, no need to guess those values because if you remember, when we have done this example using the graphical methods, we came to the conclusion that x lower is equal to 12 and x upper is equal to 16. So now we can use these two values as an x lower and x upper. So x lower is equal to 12 and x upper is equal to 16. So now the next step here, I need to calculate a new value of xr. X lower plus x upper over 2. So 12 plus 16 over 2. So x lower plus x upper. So 12 plus 16 over 2. I get a new value of xr in between 12 and 16, which is 14. Okay. Next, now I need to check my answer. Remember these two conditions in here. If the function of x lower times the function of xr greater or less than 0, then I'll start to exchange the values. So now the function of x lower is 12, xr is 14. So I need to find if the c here is 12, what's the answer of this function is going to be? And if c is equal to 14, what's the function here it's going to be? So in my case in here, when c is equal to 12, the function will retain the value 6.067. And when the function is equal to 14, I will find the answer is 1.569. I will give you a few minutes to try those values because I want you to do the example. Grab a calculator, put the value first time 12, you're supposed to get the answer, it's 6.067. And second, try the value of 14, you're supposed to get the value of 1.569. Okay, so now you get these two values, you are going to times together. So remember that we need to check if the function of x lower times the function of xr is greater or less than 0. So in my case in here, when the function of x lower, the function of 12 times the function of 13, I get the answer, it's equal to 9.519. So this value here, it's greater than 0. You back here to these conditions in here. If the function of x lower times the function of xr is greater than 0, next iteration, what's going to be happen? X lower will take the value of xr for the next iteration. So this means for my next iteration, in this case, x lower will no more is going to be equal to 12, is going to be equal to 14. For the next iteration, x lower will be equal to the value of 14. So set x lower to be equal to 14 and x upper will remain the same. Then you will go for the next iteration. Okay, I have now x lower is equal to 14 and x upper is equal to 16. So I'm going to calculate a new value of xr. So a new value of xr is equal to 14 plus 16. So 14 plus 16 over 2. I will get the new value of xr, it's 15. Okay, remember that you have to calculate the error. You need to calculate the error. xr new, now xr new is equal to 15, xr old is equal to 14 over xr new, which is 15. So you're going to get the answer. It's 15 minus 14 over 15. The error is 6.66. And remember, it's the example is asking you to repeat till the error it's less than 0.5%. You are getting the answer, it's 6.6. So this means you need to iterate one more time. So now, again, you are going to ask the question back again. If the function of x lower times the function of x are greater or less than 0. So now x lower is 14, xr is 15. Get the answer from the function. So now you can see that it's the answer from the function is came up as a negative value. It's less than 0. If it's less than 0, so it's mean for the next iteration, x upper will take the value of xr. xr is 15, so that's mean x upper no more is going to be equal to 16, it's going to be equal to 15. And x lower is equal to 14. So now you can see how is I am trying to narrow or bracket the values to achieve. The first, I'm starting this example. I start with the x lower is equal to 12 and x upper is equal to 16. Now I end up of x lower 14 and x upper is 15. So I am making narrow the search. Okay, so now for the next iteration or the third iteration, you are going to calculate a new value of xr using those new values. So 14 plus 15 over 2. So you get a new value of xr. So it's 14.5. So this is the new value. So you can calculate the error. A new value of xr 14.5 minus the old value of xr 15 over 15.5. So you can see that is now the error start to be reduced. It's 3.4, but it's still not matching 0.5. So you are going to iterate one more time. So how many times you are going to iterate? You are going to be iterate about 6 times till you are going to get the error it's less than 0.5%. So when you find the error it's less than 0.5%, or the relative percentage error because I have the true value is less than 0.5%, so you're going to get the answer it's 14.8. This is the value that make your function here is nearly equal to 0. Remember that we are saying that it's the true value. We need to get the answer it's 14.78, but because the error still there's an error, it's 0.4. We are getting the answer is 14.81. It's closer to the value, but still there is some degree of error in here. Okay, so this is how to get the what you call it, it's the bisection methods, and this is how to solve. I solved with you the example. If you have any questions, please ask. If not, I want you to do the exercise by yourself here, and I will give you the time. I will give you about 10 minutes to solve this exercise, then compare your answer with me. So what you need to do here, you need to find the roots of the third order polynomial using the bisection methods. In the interval of x lower, it's 3.75, and the value of x upper, it's equal to 5. And the tolerance value of error that you need to calculate, it's less than 0.5%. You have any question? I'll give you 10 minutes to solve this and show you the answer afterwards. Any question? Is it clear?
No, sir.
Okay, so I want you to list down in a piece of paper, write the function and write the answer. the initial value and also the tolerance value of error because I want to give you the procedure. So write down the function and write down the initial values, the tolerance value of error, because I want to show you all the time the procedure of the bisection method. Okay, you can check your answer. So you can see it's the value of XR that make this function. Actually, it's the true value that can make this function will be equal to 0 is 4. If you put 4 for all the x's, you're going to get the answer is equal to 0. So you're going to iterate till the error is less than 0.487. So less than 0.5, you're going to stop. So the exercise is asking you to iterate till the error is less than 0.5%. So when you achieve this answer here, 0.48, so it means you already achieved the answer. So you are looking at the value of XR, it's 4.0039. So if you are having like about 3 iterations with the same pattern values, so this means you are in a good track to solve the exercise and you already understand the method itself. Any questions?
No, sir.
Okay, so let's move to the last method for today, or the bracketing methods. The one here we call it is the false position methods. So the false position method takes into account the magnitudes of the function at the lower and the upper bounds of the function x lower and the function of x upper. For example, if the function of x lower is closer to the
Sir?
0 than
Sorry.
function of x upper. Yes.
The slide.
Okay, sorry. The slide. So the false position methods is, as I said, it's takes into account the magnitudes of the function at the lower bound x lower and the upper bound x upper. So for example, if the function of x lower is closer to the zero than the function of x upper, so this means x lower it's likely it's closer to the xr than x upper itself. So the result is going to be an improved estimates of the roots. So what does it mean here? It's improved estimate of the roots. False position methods, it's more faster to find the roots than the bisection methods. Why? It's because the nature of the method itself is to find the value of xr. Remember, is for the bisection method, most of the time when we are using bisection methods, the value of xr, most of the time it's in between the value of x lower and the value of x upper. But for the false position methods, we are finding the value of xr based on the linear interpolations between the value of x lower and its function and the value of x upper and its function. So what we are doing in here, we are making a line between the value of x lower and its function and x upper and its function. So we are making this linear interpolation. So this linear interpolation is going to be crossing the x-axis at this point, and this point we call it is xr. So this is the difference between bisection method and false position methods. Here, we are not having the xr in the middle between x lower and x upper. No, we are having a line. This line, we call it, it's the linear interpolation between the x lower and the function and x upper and its function. So that's why it's more faster than the bisection methods. As when we are going to do the example and the exercise, you are going to see how faster is it. Okay, so what we find here when we are making the linear interpolation, it's going to be create for us a line. That line is crossing the x-axis at this point, which is this point supposed to be is the root, but actually it's not, because the root here it's at this function when is the function or the curve is crossing the x-axis. That's why this method we call it it's false position method, because we are assuming that this is the real root of the function, but it's not. Okay, so what we are trying to do now, we are trying to shift this line to the right to make this dot here matching the real root. Okay, in this case in here, most of the changes is going to be happen at x lower because x lower is morely closer to the value of xr. Okay, so now the question is how you are going to find the value of xr, or how you are going to make this linear interpolation using this equation here. So to calculate the value of xr, it's not simple like bisection methods. We are going to use these equations to create for us the linear interpolation. X upper minus the function of x upper times x lower minus x upper over the function of x lower minus the function of x upper. Okay, again, you are going to calculate also the approximate error if you have a new value of xr minus the old value of xr over the new value of xr. So this is also considered as an iterative method. So how to solve, or what's the procedure for the false position methods to be solved? First, you are going to choose the value of x lower and x upper, but actually it's these two values is going to be given to you. And you are going to calculate a new value of xr. How to calculate it? Using these equations in here. And again, you are going to use the same criteria, or you are going to say that you are going to replace the value of xr, whichever of the value of x lower or x upper yields a function value with the same sign as the function of xr. Whether you are going to use this or you are going to use the same methods of bisection methods. If the function of x lower times the function of x are greater or less than 0, you can follow the same. Okay, so let's see this one when we are going to solve the same example. So we are following the same example, and we need to iterate till the error less than 0.5%. Remember that our reference number or the value of xr our true value, we need to achieve the answer of 14.78. This is the value that if you substitute here, the function will be equal to a 0. Okay, so now let's start. At the beginning, x lower is equal to 12 and x upper is equal to 16. So now when x lower is equal to 12, the function will return the value of 6.066. And when x upper is equal to 16, the function of x upper is negative 2.26. So now I can find a new value of xr. So xr using this equation here, x upper minus the function of x upper times x lower minus x upper over the function of x lower minus the function of x upper. Look in here. From the first iteration here, I'm getting the answer of 14.91. This value is somehow closer to the true value from the first iteration. That's why it's more faster than the bisection methods. Okay, so now how you are going to make a decision? You are going to look at the function of x lower times the function of xr, whether it's greater or less than 0. So in my case in here, the function of x lower times the function of xr, it's less than 0.5. So this means you are going to less than 0. So this means x upper will take the value of xr. Okay, so x lower will remain the same 12. X upper will take the value of xr, which is 14.91. Then again, you are going to find the function of x lower and the function of x upper. Okay, then you're going to calculate a new value of xr. So the new value of xr, you are going to calculate using those values, 12 and the value of x upper and the function of x lower and the function of x upper. You are going to put these values inside the function to get a new value of xr, which is 14.79. If you look at this value and compare it to the true value, it's almost close. So now you can calculate the error. A new value of xr, 14.79, minus the old one, which is 14.91, over the new one, the error is 0.79%. So this means one more iteration, and I think I'm going to achieve the answer. It's less than 0.5%. Okay, let's go now for the next iteration. So for the next iteration, I need to find the function of x lower times the function of xr, whether it's greater or less than 0. So in my case in here, still less than 0.5. So this means again, x upper will take the value of xr. So still this one is 12. This is 14. Find the function for both values and calculate a new value of xr. So I get the answer of 14.78. If you look at this value is exactly the true value. So now when you're going to calculate the error, the new value of xr minus the old one over the new value of xr, the error is 0.08%, even less than 0.05. So this means this is the true value, almost we achieve it, and 0.08, it's less than the tolerance value of error, it's acceptable. How many times we iterated this example using the bisection method? We are iterating about 6 times using the bisection methods to achieve a value of xr which has some degree of error, which is not closer to the true value. But we are iterating about 3 times using the false position methods, and we are achieving an answer of xr. It's almost matching the true value, and the error is more less. So that's why it's false position methods. It's more accurate and more faster than the bisection methods. Okay. Do you have any questions about the method itself?
No, sir.
Okay, so the last thing for today is the example. It's inside the slide and also from the textbook. You can try it, but I'll give you about also 5 or 10 minutes to solve the same exercise. Remember, it's our true value. To solve this one, we need to get the answer. It's equal to 4. If you put the value of 4 in all the x's here, x cube and x square and x, you are going to get the value is equal to 0. Here also, for our first example, when we are try this example using the bisection methods, we are iterating about 6 times to get the error less than 0.5%. Now, when you are going to solve this exercise using the false position methods, you are going to iterate a few iterations, about like 2 or 3 iterations, then you are going to get the exact value and the tolerance value of error less than 0.5%. I'll give you 10 minutes to solve, and this is the last thing for today. And I'm going to show you the right answer after 10 minutes from now. Okay, try it. If you have any questions, please ask. Okay, let me show you the answer. I hope most of you are getting the same. Okay, remember this is the answer from the bisection methods. It's about 6 iteration. Doing the same example or the same exercise using the false position method, just only within 3 iterations, you are going to get the answer. And error, it's less and it's more accurate answer. So XR, it's 3.99. It's almost 4. With the error, it's less than 0.5, 0.3. I hope most of you are getting the same answer. So that's all for our class today. If you have any questions, please ask. If not, so I'm going to see you, inshallah, for the next class. But it's since the timetable is changed, some of you are going to have class on Thursday. For those people that are going to have the class on Thursday, can you attend same like the previous timetable, like on Friday? On Friday, I'm going to have a class from 8 to 10. And also I can make it from 10 to 12. That's only to explain about the class on Thursday. Or if you don't want to have any replacement class, I can upload for you some videos about the open methods in your future platform. So tell me what you prefer.
Upload the class material.
For those, yeah. Okay, so I will upload for you some. I will upload for you the slides and also some videos about how to solve the methods of open methods in your future. And I will give you the information in the WhatsApp group. Okay. So before you leave, I want you to write your name and student ID at the chat box for the attendance today. Your name and student ID. Thank you very much, all. See you, inshallah, on Friday.
Thank you, sir.
Thank you, sir.